Hello, this is problem set number 3, problem 2. The process ABC shown in the PV diagram involves 0.0175 moles of an ideal gas. Part A, what was the lowest temperature the gas reached in this process, and where did it occur? Okay, let's start with part A. So part A, we want to find the lowest temp the gas reached in the process. Right, and what was our process? Our process was from A going to B, and then B going to C, right? We went from state A to state B and state B to state C. Okay, first let's write down our givens. We are given that our mole is equal to 0.0175 mole, okay? What else are we given? Oh, we're also given the values of pressure and volume at our three states. It's state A, state B, and state C, right? So let's write those down. So pressure A is equal to 0.2 atm, right? That's right here. Volume A is equal to 2.0 liters, okay? And we see this is an isobaric process, right? Or sorry, isochoric process, meaning that the volume is constant, didn't change. It's a straight vertical line. So pressure B is equal to 0.5 atm. 0.5 atm. Volume B is equal to, like I said, it's a isochoric process, so volume stays the same from state A to state B at 2 liters. Pressure at C is equal to 0.3 atm, right here. And volume at C is equal to 6 liters. Okay, so these are our givens. And recall that the ideal gas law which is PV equals nRT, right? In this case, what are our constants? N is constant and R is constant, right? And we want to find the lowest value for T. We know what our P is and our V, right? So if these two are constant, N and R, they don't change. The only variable on the right side of the equation is T. That changes. And it changes depending on the given P and V, right? If you multiply P and V, whatever greatest PV value is for the three states, state A, state B, and state C, that will have the greatest temperature. And whatever the lowest factor is when you multiply P and V for the three states A, B, and C, that will be your lowest T. So let's multiply out our pressure and volume for state A first, okay? If you multiply PA times VA, we would get that is equal to 0.4 atm times liters, right? Okay, and for state B, if you multiply the pressure and volume at state B, that would be 0.5 times 2, that is PB times VB, that is equal to 1.0 ATM times liters. Okay, and same thing with state C, multiplying the pressure and volume at that state, we would get 1.8 ATM times liters. All right, so let's see which has the lowest value of P times V. Then that will say, because N and R are constant, that would be the lowest temperature value, or T value. All right, we see we have 0.4, we have 1, and 1.8. So the lowest value between all those is this guy, 0.4 ATM times L. So because it has the lowest P and V value, we would have the lowest temperature at state A right here. Okay. So now that we know which state has the lowest temperature, how do we find the actual temperature of this state? Again, we're going to use our ideal gas law, but this time we're going to customize it for state A. Okay. So state A would be PA, pressure at A, times volume at A is equal to moles times the constant R times temperature at A. Okay. PA is given, that is 0.2 ATM. VA is 2.0 liters. Then that is equal to the number of moles that's given right here in the problem. So 0.0175 moles times R. Oh, yes. So R, we have two values for R, correct? Let me find those values in my notes. Okay. So I think you guys should probably have this in your cheat sheet, but R is equal to either 8.31 joules per mole times Kelvin, or it's equal to 0.08206 liters times ATM over mole times Kelvin. Okay? These two are equivalent. They're both equal to R. They just have different units. One has joules on the top and the other has liters times ATM at the numerator. Okay? And I will choose which constant R I use based on the units that I want to cancel out. So in this problem, I have ATM, liters, and moles. So I'm going to use this value of R right here. All right. Okay, so R is equal to 0.08206 liters times ATM over mole times Kelvin. And that will equal to temperature at state A, okay? And if I rearrange this and do algebra and plug it in my calculator and cancel out the units, I would get that the temperature at A is equal to 278.5 Kelvin, okay? And that is the lowest temperature the gas reached in the process. All right. And for the sake of the video, I will write everything that I write in blue. That's something that I think you should have on your cheat sheet. Okay? Anything with blue ink will be what I think would be helpful to have in a cheat sheet. All right? Okay, so let's move on to part B. I'm gonna make this a little bit slower, smaller, I mean. Yeah. Okay, so part B. How much work was done by or on the gas from A to B and from B to C, right? So what is the, let's say, the work system from A to B, and what is the work of the system from B to C? okay? And work system is the work done by the gas. Excuse me. It's the work done by the gas. Work environment is work done on the gas, okay? So, but either one, according to the question, you could choose either one, work done by the gas or work done on the gas. I'm going to choose work done by the gas, which is work system, right? Work done by the system. Okay, so let's look at our graph. We see that from A to B, we have an isochoric process, which is constant volume. And recall that work is the area underneath the curve of the PV diagram, right? And as you can see, we have a vertical line, so there's no area underneath the vertical line. And just because of that, I know that the work done by the system from A to B is equal to 0, right? And by the way, work for any isochoric process, right? That means any process from A to B that is constant volume, any isochoric process, the work is 0, okay? So let's write that down. For any isochoric process, work equals 0. Isochoric is constant volume, okay? All right, so now let's go to try to find the work from B to C, this guy. From B, state B to state C. Like I said, the work is the area under the curve, right? So here we go from B to C, and the area under the curve is this guy right here. From here to here, from here to here, this area, right? And actually, we can easily calculate that because that's just a rectangle and a triangle, right? We've got the rectangle here at the bottom and the triangle here at top. So let's calculate that. Work system, and the work is positive because we go from B to C, so volume expands, right? Okay, so work system from B to C is equal to the area. Let's start with the area of the rectangle right there. So the area is base times height, right? And that is, so there's two. There's a rectangle area, and the second one is a triangle area. So let's start with the rectangle. For the rectangle, we have base times height, which is equal to, the base is 6.0 liters minus 2.0 liters times height. That is a height of 0.3 ATM, right? So that is equal to 1.2 liters times ATM. And for the triangle, we have 1/2 base times height is the area of a triangle. So that is 1/2 times the base, which is 6.0 liters minus 2.0 liters. That's this guy, right? And then the height is just this guy. So that is 0.5 ATM minus 0.3 ATM. Okay? And if I plug that in my calculator, that is equal to 0.4 liters times ATM. Right? Now I have to add my area of the rectangle plus the area of the triangle. So the total area is 1.6 liters times ATM, right? that is that is my work done by the system from B to C. And in physics, or at least in the lecture videos and in our homework problems, usually the unit we used for work was joules, right? So again, this is another thing you should have in your cheat sheet if you don't. But joules, another way to write the unit joules is to write it in kilogram times meter squared over second squared, okay? Another way to write pascals, okay, is kilograms over meter times second squared, okay? And 1 liter is equal to 0.001 cubic meters. Okay, that's volume from liter, unit of volume liter, to unit of volume cubic meters, right? They're both a unit of volume. And for pressure, 1 atm is equal to 1.01 times 10 to the 5th pascals. Okay, that's from 1 unit of pressure to another unit of pressure. All right. So let's convert this value, this unit, and turn it into joules, which is our usual unit for work. All right, so I'll use green, right? I've got 1.6 liters times ATM. So I'm gonna say 1 liter is equal to 0.001 cubic meters. I'm just canceling out units, right? I'm converting it to the units I want. Okay, and 1 atm is equal to 1.01 times 10 to the 5th pascals. Okay, so if I cancel out my units, atm, liters, I would get an answer of 161 pascals times cubic meter, right? Those are my two units left, pascal and cubic meter. All right, and as I mentioned here, 1 pascal is equal to kilogram over meters times second squared. So I'm gonna change my units to equal 161, and instead of pascals, I'll say kilogram over meters times second squared. Then I also have this cubic meter that I won't forget, so times meter to the 3rd power. And I can cancel things out, right? I'll cancel out this, and this becomes to the 2nd power. So then I'm left with equals 161 kilograms meter squared over second squared. Oops. Over second squared, right? And what is that? Kilogram meter squared over second squared. That is equal to joules right here. Kilogram times meter squared over second squared is 1 joule. Okay, so I get that I have 161 joules as my work from my system. Work done by the system from B to C, right? Okay, and recall if you wanted to choose work done on the gas, which is the work environment, then we would just remember that the work done by the environment is equal to negative work done by the system. Okay, so if we chose work done by the environment, work environment from B to C, then that would equal negative 161 joules, right? That's only because of the direction. As we see here, the volume we see here the volume expanded. It went from 2 to 6. Okay, and that's why the work of the system is positive. All right, now to part C. If 215 joules of heat was put into the gas during state ABC, during the transition states from ABC, how many of those joules went into internal energy? Okay, what is internal energy? Internal energy is the same thing as thermal energy, right? So internal energy is the same thing as thermal energy, or delta ETH. Okay? Those are synonyms. They're the same meaning. Okay, so let me just write down. So Q that was added, okay? If 215 of heat was put into the gas or into the system, that means our Q is positive. So Q equals positive 215 joules. Q equals positive 215 joules, right? And we want to know how many of those joules went into internal energy or thermal energy. Well, what equation do we know from chapter 19 that deals with heat, Q, heat transfer Q, and internal energy or thermal energy? That's the first law, right? So our first law, oops, let's use brown. So the first law of thermodynamics is delta ETH, or internal energy, right? Otherwise known as thermal energy, change in thermal energy, or change in internal energy, is equal to Q, which is heat transfer, minus work done by the system. Okay? And right now we want to find out how much energy went into thermal energy, right? Well, let's find out. So if this is what we're looking for, and this was given, right? Q equals 215, and work from the system we know, right? Work from the system from ABC, we have from A to B, work was 0 because it was an isochoric process, or constant volume right here. And then from B to C, we calculated the work here, right? That was the area of the triangle and the area of the rectangle. Okay? So, okay, let's plug the stuff we know in. So delta ETH is equal to 215, which is our Q, 215 joules, minus work done by the system. And again, remember, in our case, work done by the system is actually two things, which is work done by the system from A to B, or 0 joules, right? 0 joules, plus work done by the system from B to C, which is 161 joules, plus 161 joules. Okay? And so that would equal to 215 joules. Obviously the term here is 0, so that's, we can ignore that. Minus 161 joules is equal to our change in thermal energy. And if we plug that in the calculator, we'll find that the change in internal energy is equal to 54 joules. Okay, and that's the final answer for part C. Again, guys, I hope everything here in blue, with the blue ink, you have in your cheat sheet, right? So that's these guys. R, the constant R, and the two values. And when you use one unit versus the other, when to choose is when, depending on the units of the problem and what you want to cancel out. Okay? And then these two, joules and kilograms over meters squared over second squared, is interchangeable. Same with pascals and kilogram over meters times second squared. And then these two are just conversion rates. So you use this to transfer from one unit of volume to another and one unit of pressure to another. Then the last thing to remember is work environment is equal to negative work of system, right? So if you have the value of one, you can have the value of the other, just with a different sign. Okay, thank you.